You will.
Yeah, I went swing dancing.
You should have taught it.
It's one of those things that,
Yeah.
yeah, it's jazz music. I mean, if you don't like listening to live jazz music, I take that as more of a preference issue than necessarily other thing.
Find that as a personal track, my character.
Well, character,
No,
maybe not.
You don't like that.
Yes, all right. So I want you guys to recall something. I have spent a lot of time thinking about how to present this information to you because when I self-taught through this, it was kind of horrible. And so in context of what we've already done, what we said was, let me take a curve and we call a curve, say, C. And I want this curve to be given by a vector. Essentially, this is a parameterized curve. And then I just say, well, this is the x component is a function with respect to the parameter t. The y component also varies with the parameter. And the z component, if you have it, varies with the parameter. And then the curve is going to start and stop basically when we start and stop the parameter. So we start the parameter here and then end the parameter. And then the main idea has been, okay, this produces essentially in three-dimensional space. So if I have like x and y and z, what this spits out is I get some sort of a starting point in three-dimensional space and something that kind of traces itself out with some sort of orientable direction as t increases. And so this is the idea that we started with, is here's this new idea, let's start putting curves into space and then seeing how the curve is going to interact with calculus ideas. And so now what we're going to do is we're going to extend this idea into a two-dimensional idea. Instead of it being a C, which is just some curve that's been given by a description and by some sort of a parameter, we're going to have a plane, or not necessarily a plane, but a surface that's going to be given essentially as a vector that instead of varying with only one parameter, we need two parameters because it's going to come from two dimensions. So now, instead of calling it C, when we're talking about this surface idea, we're going to call it S. So S given by a vector, so R. And now instead of just T, right? R of T implies it's just a curve. Now we have a surface, so we need two variables. We'll call those two variables U and V. Now, the inside will actually kind of be pretty parallel in structure. In other words, the X component is some function relating the U's and the V's, the Y component relating the U's and the V's, and the Z component relating the U's and the V's. And just as we had to specify what the parameters were being bounded by, well, we do the same exact thing. The only difference is now we just accommodate for one more degree of variables. So we have A less than U less than B, and then we also want to bound the V by something. So we have some C less than equal to V less than equal to B. And you'll notice that this actually is how we describe rectangular regions. Granted, is this in XY plane? No, it's in UV plane, but it's still a rectangular region. So what we can do is, here's what's kind of visually going on. If I take, let me draw this a little bigger so I can see well. Suppose this is U, suppose this is V. So this is not XY space, but this is UV space, okay? And suppose A is like right here. Suppose B is right here. Suppose C is somewhere down here. And maybe D is up here. So these are just constant bounds. Then if I'm talking about the region essentially that's given by A less than U less than equal to B and then C to D, that's some region R as all points U and V. And then this is going to look familiar to how we were talking about the double integrals over the rectangular regions. We'll just say A, again, is less than equal to U is less than equal to B, and C is less than equal to B is less than equal to D. And if we're going to draw that, can you see how this is going to sketch out? So this So this region R. And I shouldn't leave it dotted technically, I just put solid bars in so we know that it's inclusive on the. Okay, the thumbs up, if that's good.
It's a weird sounding input.
Okay, what, and then we take the parameter and then we turn it into, it's gonna turn into the surface actually looks like, so. If I have then three-dimensional space, here's my X, my Y, here's my Z. And then if I have some sort of some surface that exists in 3 dimensions. And so it's X. And the way we get from here to here is through the parameterization S given by R of UN. So we take points in here in the parameters with respect to the parameters, and every single one of these points gets associated with some point on the parameterization. So for example, if I'm interested in, boom, this point right here in UV space, in other words, some point in R gets mapped over to its corresponding point on the surface. And then like say, obviously, this isn't drawn, this isn't supposed to be a one-to-one correspondence. I'm not trying to be like here in the sense of literally that point was always going to go over there. But the idea of, okay, now then some other point would be the vector that maybe gives you this on the surface. So I'm trying to show you is that what's considered in the input space, it's turned into the vector that then spits out into where it's going to go in the surface that's in 3 dimensions. So this can be handy because then we can describe a surface that is not necessarily actually a function, because this surface is allowed to wrap on itself and all sorts of stuff, given a parameterization. In the same way that curves, and when you parameterize, it can be like helixes and slinkies and all sorts of funny things, with the degrees of freedom given through just governing the vectors. And so we're letting the components of the vector get spit out be governed by where we are at in this kind of control pattern. Okay. So far, so good.
For no reason particular, what's your favorite flavor of cake?
My favorite flavor of cake is that I don't enjoy eating cake.
Yeah, you prefer what do you think? What is your preferred dessert?
I enjoy eating kimchi.
Kimchi?
Yes. And if you're gonna get kimchi, oh, I'm going to pause the recording. So. If we're good with this, I'm going to give you the equations for the common parameterizations for cylinder, cone, and sphere. You could technically go through these derivations. Last year, I did go through these derivations, and then guess what? It didn't help the class. So guess what we're not going to do today? I like to think that I learn from my mistakes like Iron Man. Right? That's one at a time, and it usually takes a critical failure for things to help me recognize that it doesn't work. But it allows for improvement. The what?
Same thing for Iron Man.
Okie dokie. Yeah, so I'll just give you these equations so you have it to do your piercing homework. And then if you like need more references, the textbook has like a little appendix for these. But these are kind of the important ones. So the cylinder, if we're talking about a cylinder and that shape existing in 3 dimensions, if you want to parameterize what that surface is with like a vector, cylinder is given by R of UV is equal to A cosine U, A sine U, and V, where 0 varies with U up to pi, and v varies from 0 to the height, which we can just call a h. So I hope you can see that u is acting like a theta in this case. It's pretty straightforward, and the v is acting like a z value, like how tall you are, and you're spinning in a circle. There's a shocker that a cylinder is a parameterized circle that's just been lifted up through a third dimension. Yeah, it's pretty straightforward. Okay. And then the cone. Actually, let me give it a little bit more space. Cone is going to be a little bit funnier, but just because of its trigonometry stuff. It's essentially it's going to be a times v over h for cosine of u, and then a v h sine u, and then v again for just the height, where we're varying u again as if it was a theta, so 0 to u to 2 pi, and then the v is again just like the height. The cone. And the sphere, I actually like the sphere one because it is copying and pasting spherical coordinates. So for a sphere, AV over H, AV over H, AV over H. I am sorry, Chloe. I will
Rectify.
rectify. That better?
Barely.
Don't. N. That's N.
If anything's confusing, it's your sign of you.
Okay. That better? Yes. Okay. It's just like a secret society of what was his handwriting actually saying? Like pulling together like a mystery documentary on what the definition said. Okay, so A. Normally, so just how like the x was rho and then sine phi and then cosine theta, we're basically going to make all of the phi u's and all of the thetas v's. So A, instead of sine phi, it'll be sine u, and instead of sine theta, it'll be b, which makes the y component then just a sine u sine b. And then that makes this last one a cosine of u. End of the vector, and then because we basically just made u the b, so 0 u to pi, this b is the one that stops at pi and theta goes all the way around. So 0 is equal to b plus 2 pi. Okay, so yeah, that's that. Okie dokie, so if you need these references again, they're in the textbook. This is just to get you to Pearson, but this is not the most important thing that we talk about. Cool. So snip a picture or something. Cool. All right, now it gets a little bit theoretical. So here I want you to buckle in with me, okay? Follow along, take very good notes here. Anything that I write on the board, I need you to have on your paper. Okay. Recall when we were doing the curve. In other words, we were doing just a curve. We were taking little bits of the surface area changes. And then what's happening over those little bits and pieces, that was the very thing that we're taking a sum of. In other words, small little pieces of parameterized arc length. Now it's going to change and we're going to get small little tiles, but they're no longer necessarily rigid tiles. These are like little cloth. So it's like if you cut a square out in say denim, and then you're holding it up. You can orient that a bajillion different ways. It doesn't necessarily hold that rigid, like actual square position. But that in itself is like a patch, this little partition piece of surface area. And so what we're doing is we're summing up all of these little patches that are sewn together into like a quilt, which is the surface. Does that make sense? Okay, so what we need to do is draw a picture and try to figure out what we're trying to describe mathematically. So here is an anchor point for reference. And we can call this point P of xk, yk, zk. K is indicating this is an arbitrary choice and of which point we're talking about on the surface. And then here, I'll elaborate on what these vectors are, but here is T sub u times this delta u. And then over here is going to be a vector T sub v delta v. And then that's going to produce the bounds for essentially this patch that we have here. So here's the patch of surface area. Everyone can see that. And then the cross product is going to be orthogonal to the both of these. So it's going to be TU cross TB, that vector. And then if I want to give myself reference how this is interacting in three-dimensional space, so say this is like your X, and this is your Y, and then this is your Z. And then so this would actually be like close to the surface, approximating the actual surface. So the actual surface might be maybe curving down a little bit underneath like this, but we're looking at just a partition of this surface area. Now let's actually talk about what I mean by T sub u as a vector, or T sub v as a vector. T sub u as a vector and T sub v as a vector, these are tangent vectors. Tangent, not units tangent, just tangent vectors. To the surface S, corresponding to u and v respectively. So whatever those two variables are, where they're tangent, and tangent means slope, so there's going to be a derivative involved. And just so we know what we're talking about, the surface S, this is the kth patch. So this patch right here I can label, this is the kth patch of what we're going to call this SK. So the overall thing is the whole patch. We have, just for reference, the parameterized surface. So parameterized surface S given by the vector R, U, and V, which is equal to X, U, V, Y, U, V. What's the third component going to be? U, V. And then obviously this has its bounds. I'll just put that here. So A is left equal to U, left equal to B, and G left equal to V. And then now what we're gonna say is if the TU and the TB are tangent vectors of S with respect to those variables, then what that means is when I am saying TU like that, tangent is going to be derivative and a derivative of S, but S has two variables. And so I need to take a partial derivative instead of a regular derivative of the R U. Which, if I go through this entire vector and I differentiate only with respect to the u's, I'm going to get the partial derivative of whatever x is with u, whatever y is with u, and whatever z is with u. So thumbs up if that's good. So how to go from tangent to, and come in conjunction with what we have at the surface into this vector right here. And then visually it's nice, right? Because tu is just dx u, y u, z u. And then would it make sense if I told you, well, actually, I'm not going to tell you, you tell me. So TV is going to be what? Yeah, partial derivative of R with respect to J. And so the first component is going to be what?
XV.
And then the next component?
YV.
And the last component?
ZV.
There you go. So that's all there is to it. So we have those pieces now. And basically for the tangent, if I took the partial derivative of R with respect to u, Okay, so I'm talking about the TU right now. Sorry, this is approximating because given as the derivative, that's like actually precise, but what we're working with the past is an approximation, so I need to do an approximation sign. Is about 1 over this nudge in the u direction times the change in the r with respect to u's direction. So r, u plus some nudge in u, but the v is going to be held constant, minus r of u and v. And if we hold that to be true, and we understand that this tu is going to be over here, multiplying both sides by delta u is going to result in having, we have tu, which is this, times delta u. And then this is approximating the amount of change that occurs in r as we nudge u some amount. So r of u plus delta u v minus r of u and v. So right here, this is the change in r corresponding to u. I should say delta u, really. Yeah, in Calc 1, this is kind of how we construct a much simpler idea with derivative definition. But the reason why we want this is because that's the very thing we were talking about. We're talking about this direction scaled out by this nudge in the u direction on our K patch. So we need a way to talk about it. And so now we can talk about it with respect to the actual parameterization. So in a similar way, I'm not going to repeat all the steps because it's the same idea. We're going to end up for the TV delta V. That TV delta V is going to be TV delta V ends up being the change. So now U is being held constant, right? So we don't care about the nudge in U. So when we nudge V, V plus some change in V minus R without any change in either of them. This right here would be the change. And R corresponding to delta V. So change in R corresponding to delta V. Thumbs up, that's good. Oh, thank you. Yes. Because this is technically an approximation. I'm thinking too far ahead. Because we're going to take a limit as the deltas go to 0, and then it'll become equal to 0. Good catch. That would have bothered me in the recording. All right. Okay, cool. Because now what we're going to do is we're going to start talking about the area. So we've built the language for the pieces. So you're going to want to have this stuff written down so you can kind of turn back and refer to the characters, essentially. Because this is a lot to memorize right now. Okay, going once. Going twice. You good, Axel?
Yeah.
Okay, just take a grab it.
Yeah.
Grab it. And sold to the mayor. Okay. Accidentally erased the one part of the picture I needed for the next part. Let me just redo the plan. Okay, this is TU cross TV, and then let's see. Okay. So now what we're going to do is there's a formula essentially that relates the cross product to the area of a parallelogram. And well, we have two vectors and their cross product, and then this area, essentially the magnitude of this area here. And so the area of the K patch I almost wrote patching. Patch
Before patch.
area
Oh,
of case patch. So this is the case patch, right? That's case. Yes.
okay.
Is going to be the magnitude of this cross product between TU and T, well, more specifically, these vectors involved, so it'd be TU times delta U cross TV times delta V. And by theorems, this is going to be also just, we can take the constant stuff out, the TV, oops. TU cross TV. And then times the delta U and delta V. This is approximating what we mean by now, some change in the overall surface area. So then the actual area of the patch, change of area of the surface. So this delta SK is describing the area of this region that's been kind of drawn out here. Is that good? So at least we know what the delta FK really refers to, it's the piece. And then we're going to quilt a whole bunch of these together using a sum. So that sum is going to be a sum from k is equal to 1 to n. Function evaluated at x and then uk, vk, y, uk, vk, z, uk, vk, and then times the delta s, okay. So we're going to sum up all of the contributions of the function that apply to each patch. So the quilt together, boom, you get roughly the entire thing. And so because we want to approximate what this is with respect to the TU and TV, I could say that this is approximately, so this is approximately the sum k is equal to 1 to n f of x of uk, vk, y, uk, vk, z, uk, vk. And then instead of putting the delta sk, because that's what we want, well, we've shown that the delta sk is approximately this. It's going to be the new differential, essentially. I think somebody was asking about whether Jacobians apply to vector values things when we're changing variables and such. This is going to be the closest we do in this class to actually kind of changing variables in the vector context, because this is approximating the delta s. Okay. And so the way we did in calculus go from a sum to actually something infinitely precise is we use a limit. And so do I have room to fit it all on the bottom here? Okay, I won't have, I'll have room, okay, I'll do this. So, because these just get super long. So the double integral over a parameterized surface S. So think of this as the analog to when we would do a line integral over a parameterized curve C. Same idea, we just parameterize the surface now, so technically it's two-dimensional, we need to have a double integral. Of a function x, y, z, the capital S, okay, because it's the differential of the surface area, which is patch now, not just a little bit of line segment or arc length. This is going to be the limit. And what two guys do we want to go to 0?
Delta U and delta V.
Yeah, that's the things that are the approximations. So we make our approximation changes, delta U and delta V, those together approaching 0 is going to become infinitely precise. And so we've got then the limit of this sum, k equals 1 to n, f of x, uk, vk, y, uk, vk, z, uk, vk, I keep saying UK, I'm gonna summon Dr. Lang into this class, right? And then the differential is the TU cross TV delta U delta V.
Just say,
And then by taking this limit, this is what we then get with the calculus version. Nice. Just it's a double integral over a region R, where R is describing those bounds on U, so A to B and then C to D, of the function f of x, where that relates to that, y u to v, z u to v, and then now we just have tu cross tv dA. It's just now differential. So everybody snag a picture of that, because I'm gonna need to move forward, clear this board, and give you the formal definition in the textbook. Okay, we good? Bigger miracle if the whiteboard still works after this. So the definition, all of that construction essentially is half of the section of the textbook, if you were to read the reading. And now, the thing that's gonna be the summary of the definition. Let f be a continuous scalar value function on a smooth surface, S given parametrically by R of UV, which is X UV Y UV Z UV. You're gonna see that construction quite a bit. Where U and V very okay, so instead of now listing out just the A, U, V, and then the C less than equal to V, less than equal to V, we're gonna start calling that a region R, a rectangular region R. So over the region R, which is the points U, V that are satisfied by A is less than equal to U, and then C less than equal to V, So this is just like the upgraded version of the giving the balance for parameterization for line integrals. Now we're going to also assume also that the tangent vectors given by how we define them. So TU is XU, YU, and ZU. What's TV?
X V, Y V, Z V.
And then these are, we want them to be continuous. Continuous on R. And the normal vector is going to be the cross product by definition, right? So we want the normal to be a non-zero vector. Otherwise, we don't really have a path. So TU cross TV. This can't be the zero vector, so not equal to zero vector on R. Then after all of that is met, we can say that the surface integral, the name of the section, surface integral of f over s is, and then just reiterate what we already did, which is that it's double integral s of f x y z, the capital S, because it's that path instead of just an arc length chunk, is integrating over r given by the u's and the b's as stated above of f, and now we've parameterized x with u and v, y with u and v, and z u and v. And then this new differential is the cross product of tu across tv. Okay. And now you know where this tu cross tv dA comes from. If I would have just written this definition down as the first thing in class, would it have been that predictable? Okay. If the function, again, so if the function here is just one, if the integrand is just one, then that's just giving the surface area. So if I want the surface area over the parameterized surface, I would just change f to just be one, have the quality of one, and then integrate. Okay. Okay. I'll give you this formula for Pearson purposes, and then we'll do transition over to the vector stuff, because the vector thing is the more important part. Okay. Again, all definitions are taken from the textbook. Thumbs up. Cool. This is if you're given, you might be wondering, why would we parameterize a surface all the time? What if it's actually just a normal surface, like as a function? We already talked about how to put together functions, like multivariable functions in multivariable calculus. So what happens if you're just given, like, say, z is equal to a function? So if you end up given a circumstance where you've got a function, so let f be a continuous function on a smooth surface F. Surface S. Now, instead of being given parametrically, it'll be given by some z is equal to g of x y. For points x, y in the region R, a region. Okay, do you see the difference? Here, you don't need to parameterize anything. You just have it as it is. And then there's going to be a formula relating straight from the way that you've defined the explicit surface. Then the surface integral. Surface integral of f over s. F over s is, instead of doing the parameterization, we can actually just use this trick. And we know that we get this trick and it's derived from the parameterization method, but again, it's not all too insightful as a proof, it's kind of boring. So here's the result. X, Y, now instead of putting Z here, we're actually going to say G of X, Y, similar to the, you guys remember that proof you got to do with the linear approximation, the equation of the tangent plane? So when we have it explicitly, you give that third component in terms of the first two variables. And then here's where that Z stuff comes in, ZX squared plus ZY squared plus 1 all under the square root. dA. So there you go. You have that formula. Take a picture of it. It's in the textbook. As you do your Pearson, and if it gives you an explicit thing and it asks you to use the explicit formula, this is all they're talking about. This is gonna involve plugging and chugging your G function value from the surface into whatever the given F function is, and then figuring out, simplifying the algebra here before plugging it into the integrand.
Like d of x squared plus d of y.
Yeah, these are partial derivatives. Because z is given by g. So really what I could have put is just g sub x, like the partial derivative of g. But yeah, that's good. Okay. You ready for the vector version of this? Because the vector version is somehow easier to visually understand than the scalar version. So the reason why it'll be easier is because we keep returning to this almost every single lecture, and repetition legitimizes. So recall that we had in before, we had a line. So I said, okay, I got some C, it's been parameterized, it's some R. Okay. I don't care what the R is. Essentially, what we're looking at with flux, actually, let me relabel the top for surface integrals for flux. Now I'm talking about flux. Flux, with the curve, I could start somewhere, have an oriented curve that goes in a specific direction, right? And then at every single point on this curve, like so, I'm looking, circulation is F dot T and flux is what? F dot N. So we're interested in the normal. Specifically, how aligned is the field with the normal? Because we are interested in field lines passing through the curve. So here, if I want more flux, the field is going to be more aligned with the curve. Oops. So we're essentially having more field passing through. So if I like over here, add more, here's the normal. And then if I had field contributions passing through, so it's aligned with the normal. And in general, that makes sense, right? Because if I have a bunch of field lines passing through, then we'd say there's a lot of flux. In the same way, if you were holding a piece of paper in front of you and then blow straight onto it orthogonally, it's going to exert the most amount of basically force against that paper than if you were holding the paper flat and then you're trying to blow across the surface.
Should we do that?
Yeah, well, it would go like that. But so now what we're going to do is we're going to do a similar idea. So this was, we would call these kind of sums of contributions the integral over the curve of f dot n. Little ds, that's a lowercase ds because these chunks are arc length chunks. Now we're upgrading this to more dimensions. So suppose I now have some patch, some surface in 3 dimensions. Okay. Now, given any point, so like say if I take this point right here, again, I'm interested in that normal. So if it's normal coming off of the surface, and then I'm thinking, okay, how much is the field aligned with the normal? Because if the field is piercing through my surface, essentially, or going against, so if I have like the field doing something like that and passing through the surface in that sense, well, that's pretty aligned with the normal. It's going to be a decent contribution of flux passing through my surface. And that would make sense that if you had a field contribution that say was maybe like right here, maybe it was parallel with the surface. How much of that field line is passing through the surface if it's just going to be lying flat on it? Nothing. And that should make sense because then the dot product between the n and the f would be orthogonal, so it's 0. So flux is really this measure of how much intuitively is passing through. Have you ever been fishing and you have like a little fish net and you just dip it into the water with the water's passing through it? Essentially, if you want the most amount of water to be passing through it, you're going to have the hoop of the net open toward as much as the stuff orthogonally passing through it. You wouldn't put it in sideways and the water's passing through parallel to your hoop because nothing's passing through your net, okay? You're trying to catch water, you're trying to catch flux, you're trying to make it as orthogonal to the surface as possible, okay? So that's really what we're measuring. And now, instead of being stuck with just a line, we can really do this with an entire surface and then measure how much stuff is coming out of a surface. When this is going to be super, super important in EMAG, when you're talking about electric fields and magnetic fields passing through surfaces, the way that interacts with each other. So instead of just saying a single integral over C for f dot NDS, herewith, if this is parameterized as f, then what I'm really doing is I'm taking not just one integral, I need two because this is a surface, over S, same idea though, it's analogous. Just as we're taking the integral over C, kind of like over C, we're taking this integral over the parameterized area S of essentially still contributions of f dot n ds. The only difference is that instead of being arc length ds, we're talking about actual patches of surface area, capital ds. Really, really related to each other. And sometimes what you'll see in your physics textbooks is they abbreviate NDS to be, I've seen this in most of the, at least if it's published in like the 80s in EMAG, they'll say ds vector. So that ds vector is the idea of you've got the normal times the patches of surface area. Is the transition between the one-dimensional and the two-dimensional starting to click, because that's the biggest part of this. If you can understand why we construct this in the first place, Stokes' theorem is going to have some level of relevance, because that's the main tool here. So at the moment this starts getting confusing, just stop, go all the way back to here, and think the basic game. How much of this field is going through my curve? And then simply say, okay, same exact question, slightly different environment, but it's the same exact question. How much field is passing through or is normal to surface? Okay. Right. So you just need the formula for the vector form, which I can do on the next whiteboard. So everyone get this down. We're good?
Yeah.
Okay. One more whiteboard for today. Okay, so in the same way, let me actually start by writing what we were trying to do. So recall that when we took the C, and then say, for example, f dot t ds, we went to a lot of trouble to take the t and rewrite it in terms of something else. We took a lot of trouble to get the ds in terms of the dt. So we're going to do the same exact thing for the surface integral. We want to get this thing out of the capital ds, because the ds has it right now. And the way we can do that is we can basically find a substitution. So right now, the thing that is uncertain how it relates is the normal vector n. And if you flip back in your notes to when we were drawing out the patches, that normal vector that's coming up is that cross product from the TU and the TB. So we need this to be a unit. So I take TU, TB, cross TB. And I divide a vector by its own magnitude to make it unit. So it'd be magnitude. So now our unit normal vector with respect now to these patches is the TU cross TB divided itself by its own magnitude. And this is going to allow us to then do the substitutions in the constructor. So here, this is going to take us over here. I can then say that my integral over the S of f dot n d capital S, right? ds, that patches. First thing I need to do is simplify the ds. So I'm actually not going to substitute n first. I'm going to substitute the ds, where the ds, when you look back at the definition that we constructed in the first half of class, that is integral over r f dot n, and then it's this tu cross tv dn. Okay, so remember this when we first built the definition. With this, instead of saying d capital S, we can actually just put this in for the ds. And the thing that's different is the actual integrand is now vector stuff. And that's what's going to make it related to the flux. Now we can substitute what we have with n. And I'm going to do this on a new line. I'm going to bring it down here. So down here, I've got the integral over r f dot, okay, so n is this. So let me plug that in, and it's gonna be TU cross TV over the magnitude of TU cross TV. That's N. And then I'm multiplying N by this. So then I've got TU cross TV PA. So this is essentially yes. And convenience of all conveniences again, we get two scalar quantities canceling out. So we are just left with a much more simple double integral over R with the field interacting in a dot product with this little cross product here that we can compute with the partial derivative stuff. So then the definition, the way we're going to define flux over the surface integral with respect to some sort of a field is going to be that if I take a parameterized surface F and F dot N ds with capital S for that all I can do is actually just do it in terms of the parameters U and V, which is a rectangular region, which is much easier to deal with. And that's just going to be F, the integral over R, F dot U cross T. This is the big thing. Translating a parameterized surface into being able to actually just take an integral over a rectangular region. If again, you get an explicit function, so you're not handed S where you can actually describe S not through some convoluted parameterization. They just say, hey, S is going to behave exactly like a paraboloid or something like that. Then you can just use the much easier formula, which is going to be the double integral of R minus F times ZX minus G ZY plus 8 BA. This is explicit. Are there any questions? So again, the idea is the same. This entire chapter is about F dot T ds and F dot N ds. This section specifically extends F dot N ds. So shocker. Next section going to elaborate on the curl. Now that we have a way to talk about what it means to actually be integrating over something that's been parameterized, we can now take advantage of that. We'll use that tool and then relate such an integral to a line integral. Because in some cases, it's going to be possible to evaluate double integrals over vector stuff with just a line integral.
Wait, why don't you just help them recall F dot T and F and that?
Oh,
We end up going for F dot N.
this was a conceptual thing, not to be taken literally in the construction. I should have probably just put F dot NDS. But it looks really similar because my handwriting isn't too good to like the little s's versus the big s's. But I'm just trying to get you to recall the way of thinking. So the way of thinking of when we started with this version, we didn't stop there because that's really horrible to compute with Arthur. So we're getting it in terms of the parameter t. Yeah. Cool. All right. I'll see you guys on Wednesday.
When is the exam?
It'll be right after the break. So not the what's the Monday? It's either the Monday after or the Wednesday. I'll post some. Let me stop this real quick.